In this lecture, we will discuss in more detail about the grid, that is the way we discretize the domain, and then we will also look at discretization of the governing partial differential equations. So, we are relooking at the different steps involved in performing CFD simulations. We have been discussing about problem definition, objectives of performing CFD, choice of governing equations, which involve different levels of approximation of the reality. And then in the upcoming lectures, we will talk more about the pre-processing step, where we discuss about the grid generation, and we are basically talking about a domain where the problem is defined. We want to discretize that domain, and grid generation will be the means by which we discretize it. And then we will also look at method of solving the governing partial differential equations. There are different ways of doing it. We will discuss about the finite difference method, and using suitable initial and boundary conditions, how a finite difference based calculation of the partial differential equations can be undertaken, that we will discuss subsequently. So, that involves the flow solver step of the CFD calculations. As we discuss that, we will also talk about stability and accuracy of the numerical schemes which are involved. So, let us spend more time on these two very important steps of computational fluid dynamics or computational aerodynamics. So, as we said that we have a domain where we are trying to solve a flow problem. Once that is defined, we have to discretize it in some manner. That means, we have to reduce the domain into a finite number of points or a finite number of control volumes, and then try to approximate the governing equations over those discrete elements. The process by which we discretize the domain is what is called as grid generation. This happens to be a part of the pre-processing step, in fact, the most important pre-processing step. Now, depending on your flow problem, the flow domain gets defined. For example, this is a rectangular domain where we are trying to solve a flow problem. Let us say you may actually be talking about solution of flow past a flat surface, a flat plate, or you may be talking about flow through a channel in which different surfaces would get defined as no slip surfaces or zero shear surfaces and so on. And this can act as the inlet, this can act as the outlet, or inflow and outflow, and appropriate boundary conditions have to be imposed there. But before you do all that, as you can see, we have discretized the domain into large number of rectangular control volumes, if you look at it from control volume point of view. Or you can also look at it as a large number of grid points. If you look at one of the intersection points, then that happens to be a grid point. Now, in finite difference calculations, we look at the grid points, and we make use of the differential forms of the governing equations, and then we try to approximate them at these grid points. While in a finite volume technique, for example, we will talk about these different control volumes. I have marked one of them, and then we try to use the integral form of the governing equations on each one of those control volumes and try to work out the flux transports which are happening across the different phases of the control volume. So, this is broadly how we look at the problem when it comes to solving the problem, but before we solve we have to anyway discretize, and we are going through that process in the grid generation step. So, as we saw, if the solution domain is relatively simple in terms of its geometry, we may actually have a rectangular domain like what we see here, and then the discretization is somewhat simpler. You can even think about algebraic techniques by which you can distribute the points, and that can be called as algebraic grid generation. While when the solution domain becomes more complicated because the boundaries are more involved, like you can see over here, this may be like the leading edge of an airfoil, and you are trying to wrap a mesh around the airfoil, and you are just looking at part of that mesh which is close to the leading edge of the airfoil. So, here you can very well understand that you cannot have the same kind of mesh that you had over here. So, here if you had fitted the xy coordinates, then basically the lines that you drew were either parallel to the x axis or parallel to the y axis, and then the grids were basically non-uniform. You may have noticed that they were more closely spaced near the lower boundary or near to the upper boundary, and more closely spaced closer to the inflow boundary than the outflow boundary, and so on. But nevertheless, they were parallel to x or y axis, but here that is not possible because the geometry is curved, and therefore, you can think about a curvilinear mesh, a curvilinear mesh. And further we are saying it is a structured mesh. Now, what do we mean by that? You can see two different families of lines which are forming the mesh. One which is approximately moving in the tangential direction, while the others are moving approximately in the radial direction. And therefore, if you pick up any point, any grid point which is formed by the intersection of these lines, then you can find only one line from each family which crosses it. So, one line from this family and one line from the other are crossing that particular point. So, each point can therefore be formed by crossing of one line from each family. That is basically what we have in structured grids. For more complex geometries, you may not be able to handle the mesh generation problem with structured grids which are curvilinear. You may actually have to go for another kind of grid which is called as unstructured grid. And in unstructured grid, there is no restriction like this. More than two lines can actually meet at a point, like you see here. Say this is a grid point, and if you look at the lines which have converged, you have one here, you have another, so many of them converging at that point. So, there is as such no restriction on how many lines may share a point. So, that is basically an unstructured mesh. So, here you have a purely structured mesh. Again, the mesh is very fine near to the boundary, and then the mesh becomes gradually coarse as you move away from the boundary. Why do we do these refinements? We do them because we want to capture the gradients of the flow field. You can very well understand that this kind of a mesh will be most well suited for a viscous flow calculation. So, a boundary layer will be formed on the surface, whether you are solving a problem like this on a flat plate or through a channel or over an airfoil, the boundary layer will be formed. So, the velocity variation will come up over here, and that too may be a very thin layer if it is a high Reynolds number flow. So, you need adequate grid resolution. That is why a very refined mesh is used for the near surface region. As the Reynolds number increases, especially when you go into turbulent flow regimes, you will see that the small eddies become smaller and smaller as the Reynolds number increases, and therefore, you need to have a more refined mesh in such a situation. Looking at the more complicated geometry case, here you have a leading edge slat and the main airfoil section, and the gap region has been modeled. You can see that a structured grid is being used next to the surface for some distance, and then gradually it is becoming unstructured. So, roughly the region I have marked over here is filled with structured, and beyond that you can identify that it is unstructured. The same has been done even for the slat. When you have a mix and match, you have what is called as a hybrid mesh. Now, in the case of structured curvilinear mesh, there are also additional techniques which one needs to follow. That means, you can transform the problem from physical space to computational space, which may be particularly more required when you are using the finite difference technique or method. It may not be required when you are following the finite volume method, because you can actually solve for the problem in the physical domain only, though it is curved. While in finite difference method, you try to transform the problem from the physical plane which is curved to a computational plane which is nice and rectangular, let us say, where we have uniform grid spacing. That is why we transform the problem from xy plane to xi eta plane. So, the xi eta plane is basically the transformed plane. When you do that, all the governing equations have to be transformed as well. So, you have seen that in governing equations we have derivatives, partial derivatives with respect to x, y and so on. So, each one of them would have to be transformed. So, by applying the chain rule of partial differentiation, you can write down the partial derivatives in a form like this, and then you see involvement of terms like this xi x, eta x, xi y, eta y and so on. So, this can be written as xi x, this can be written as eta x, etc. So, these are called as metrics of transformation. These are transformation derivatives operating between the physical and computational space, and they are called as the metrics of transformation. So, if you try to approximately look at what they are doing, xi x term would be a ratio of delta xi by delta x, which is like ratio of arc lengths in computational space to that of the physical space. So, that way the whole problem is transformed from a curved region in physical space to a rectangular region in computational space using these metrics of transformation. Again, there is something called as Jacobian of transformation, which is defined like this, and here you see that the partial derivatives are of an opposite manner. This is obtained by reversing the role of the dependent and independent variables. You can obtain this relation. So, the J over here is what is called as Jacobian of transformation, and it gives you the ratio of areas when it is a 2D problem, or its ratio of volumes when it is a 3D problem between computational space and physical space. That means, when you transform, the areas transform in a certain ratio, the volumes transform in a certain ratio, and that transformation ratio is decided by what is called as the Jacobian of transformation. So, here it was arc lengths, and there it is ratio of areas or volumes. So, this is broadly what we try doing in the grid generation step, so that the entire domain is discretized into a finite number of points or regions, and then we try to approximate the governing equations and apply them over those finite number of grid points or volumes. Having said that, let us move to the flow solver step and do a little more detailing. As we said that we are going to look at the finite difference method in a slightly more detail. Here what we do is we try to approximate each one of the derivatives in the form of an algebraic expression. So, in order to do that, we make use of Taylor series. So, we expand a function in a Taylor series about a particular point in space or time as we need, and then we try to work out an approximate representation of that derivative. That turns out to be an algebraic expression. And then we have to take care of the truncation error which is caused because of the approximation, and from that truncation error term we can figure out what is the accuracy of the discretization. So, the first term that we have in the truncation error, that gives an indication of the accuracy of the discretization. We will find that that first term contains product of the grid spacing that we use raised to a certain index, and it is multiplied with a higher order derivative of the dependent variable. In order to work out the accuracy of the discretization, we have to have a close watch on the index of the grid spacing. We will be able to understand it better in a couple of minutes from now. What does the truncation error indicate? It determines the rate at which the error decreases as the spacing between the points is reduced. So, whether the error will reduce in linear manner or quadratic manner or still higher order manner, that depends on the accuracy of the scheme, and that is why the index of the grid spacing gets involved. Order of the difference equation indicates the accuracy with which it approximates the derivative. So, let us now show some examples. So, we are having a function f x which is going to be expanded about the point x, and we are going to go a slight distance away from that point x, which is indicated by h. So, we can apply the Taylor series approximation to obtain the value of f of x plus h, which is given by this equation. From that, if you rearrange the terms, you can get an approximate representation of that f dash x in terms of f of x plus h minus f x by h, and then you are left with many terms which we will not consider finally. So, this is what is called as the truncation error. And we have to watch out for the grid spacing h, which we are talking about, and the index. The index happens to be 1 here, and h is the grid spacing. What is the idea of the grid spacing? This is the point x. We have a neighboring point at x plus h. We can have another neighboring point at x minus h, and still more, and all of them are at equal distance from its adjacent neighbors. In that case, what we have is a one dimensional finite difference grid which is uniform. This is a one dimensional uniform finite difference grid. You may or may not spell out finite difference here. If you just say grid, that also works. Now, why have we named this particular expression as forward difference? Because we have moved along the direction in which x is increasing, which is the forward direction. If we had moved the other way from the reference point, that would have given you a backward difference, and that is precisely what you have in equation 2a, where you first expand f x minus h in a Taylor series, rearrange the terms and get an expression for the first order derivative. So, both these derivatives are first order accurate in space, because the first term in the truncation error, which is called as the leading error term, has the grid spacing raised to the power of 1. If it was raised to the power of any other positive integer n, then it would have given us an nth order accurate finite difference discretization of the first order derivative. So, with this we have a basic idea of what finite difference discretization looks like on a uniform one dimensional grid. Now, we can proceed further and try to work out many more expressions. One of them being what is called as central difference of the first derivative. What does central difference mean? We have the point x here, we have the neighboring points x plus h and x minus h, and now we are not going to go either forward or backward, but rather look at both directions and pick neighbors to help calculate the first order derivative using the weightage from both sides, forward as well as backward, in which case it is called as central differencing. So, the details are given in these equations 1 to 3, which is easy to explain. Now, you have a second order accuracy. You may have noticed that when we did forward differencing, we had these 2 points at a distance h. For backward differencing, we had these 2 points again separated by a distance h. Now, you have this point and this point participating in the formula, but then the number of grid points over which you are performing the finite difference operation is 3 points. Therefore, this is called as a 3 points stencil, while these two cases would involve 2 point stencil. So, one thing you notice is that as the order of accuracy increases, the stencil size also increases. Now, you may be wondering that why are not we talking about higher derivatives? Because for example, Navier-Stokes equation has second order derivatives in space. So, if we look at second order derivatives, can we have a way of discretizing them using the finite difference technique? Yes, we do have, and we are going to show one such discretization where the accuracy is second order. So, the second order central differencing for the second order derivative looks like this. So, you again have 3 point stencil x plus h, x and x minus h, but functional values of all 3 points have been used here, while here it is only 2 of the functional values were used. Also, the denominator now is h square, you might have seen that, and you have a second order accuracy because the leading error term in the truncation error is 2, has an order 2. Now, all this holds good as long as you have a uniform mesh. If we had a non-uniform mesh, then things would become a little more complicated. The expressions would not be so simple. Having learned the basics, let us try to apply them to some of our types of partial differential equations, which we have already got introduced to. We also learned how to classify a general second order partial differential equation in the previous lecture. So, let us try to look at those 3 different classes of partial differential equations. We begin by looking at equilibrium problems involving elliptic partial differential equations. So, what we have here is the problem of solving Laplace equation. Dependent variable is f, which is a function of x and y. We already learned that the second order derivative of f with respect to x, it is a partial derivative here, mind it. There we had learnt it as if f was only a function of x, but here f is a function of both x and y, and therefore, we are writing it in partial derivative form, but the same formula applies over here as well, as long as you keep the y coordinate constant. So, we have just included y here, but kept it constant. So, the same formula applies. In the previous case, the grid spacing was h, here it has been changed to delta x, because you have two different directions to look at. The order is of course second order. This is another way of writing it. O stands for order, order of accuracy or order of error. In this equation, it means the order of the error terms, but that also helps define the order of accuracy of the scheme. We have to similarly do it for the y derivative. So, we end up doing it here by keeping x constant, and we are moving along the y direction. So, moving along the y direction would mean that now the grid points will be like, you can say y, y plus delta y and y minus delta y. And you will see that when you apply it to the Laplace equation, that means you are going to put this form plus this form equal to 0, and then you rearrange the terms. You can write them like this. Let us not look at the superscript immediately. First, let us match the coefficients, the subscripts. So, you will see that these subscripts appear in your second derivative expressions for x and y, and there is a coefficient 4 associated with f of x y, which is f I j. Now, this nomenclature is easy to interpret from these two equations. What we do is, in the x y plane, you may mark this point as x y, you may mark it as x plus delta x y, x minus delta x y, x y minus delta y, and x y plus delta y, right. And then these are the spacings, grid spacings. Delta x and delta x here. We have a uniform mesh along x and y directions. You can also call this point as I j in the form of indices. So, I gives you the x index, j gives you the y index of that point, which obviously means that this neighbor will have an index I plus 1 j, while this would have a I minus 1 j, while as you move in the y direction, the I does not change, the j changes. So, this is how you apply the index notation. So, keeping the index notation in mind, now if you go back and look at this equation, you will be able to figure out that only thing that we have done over here is to apply the index notation, by means of which these two inputs have converged here. Now, additionally we have used a superscript where some of the superscripts are kept at a level k, while for 1 we have kept it at k plus 1. And then on the right hand side we are putting r I j, which indicates a residual. So, what do we really mean to say over here? We mean to say that there would have to be an iterative procedure by means of which we will end up solving the value of f at each one of the grid points. So, the value of f I j will be updated by averaging the neighboring grid values. This basically follows the physics of diffusion, where the influence comes from all ends. it also matches with the idea of the elliptic partial differential equation, which we had discussed earlier, that the entire domain is its domain of dependence. So, inputs come in from all directions. So, what you can figure out is that you can take the current iteration level values of f I plus 1 j, f I minus 1 j, f I j plus 1 and f I j minus 1 to generate the next iteration level values of f I j. So, what we mean to say is that the central point will be taken to the next iteration level value based on values of its immediate neighbors, which are coming from kth iteration level. So, here in order to obtain the solution, what we have to do is iterate the solutions by updating them based on arithmetic average of their neighboring values. If you have a equal grid size along x and y directions, you have a simple form that you have over here, and through the iterations the residual will go to 0 gradually. So, as we iterate, we generate updated values of f I j, and what will matter finally, what will be physically significant is the equilibrium distribution which you obtain at the end of the iterations. And as you do that, the boundary conditions have to be imposed all along the boundary of the domain. Now, these boundary conditions have to be imposed either in pure Dirichlet form or mixed Dirichlet-Neumann boundary condition form. Dirichlet form basically means you have to state the value of f, what it is at the boundary. Neumann condition means you have to state what is the value of del f del n at the boundary, where n is the boundary normal direction, which means if it is a boundary like this, here you will have to specify del f del x, because the x direction is normal to that boundary. If it is a boundary like this, you have to tell what is del f del y, because the y direction is normal to this boundary. And then you have to have a sufficiently refined mesh for a good resolution of the distribution of f. So, if you have a fine mesh, a solution will be nicely resolving the details. If you have a coarse mesh, it will be very roughly computed. So, with this we are coming to the end of this lecture, where we looked at the grid generation steps in detail once again for both structured grid, which is rectangular and also curvilinear in nature. We also briefly looked at a hybrid mesh where structured and unstructured mesh occur together, and then we looked at the basics of discretization using the finite difference method, and we applied the basics to discretizing the Laplace equation. Thank you.